Okay, is the desktop you see the desktop now? Is it everything still okay?
Yep.
Okay. Let me arrange things here. Okay. Um, so today we're going to finish talking about these sorting algorithms. Today's the last day of class. I was hoping to have one more homework assignment with using closures, but I wasn't able to find time to write one. So you've had 5 programming assignments. I think we're going to call it a day, and your grade will be based on these 5 programming assignments. And I think everyone's got it. This has been a good amount of work. So I'm not going to have an exam or not going to have a last homework assignment. I meant to have one last homework assignment about closures, but to have not had time to write one up. I'll tell you, I can tell you in words as we go along. Give you a sense of what it was. And if you're interested, you could try it because this is really interesting, useful stuff. But but as far as I'm concerned, the 5 homework assignments, if you know, if you haven't turned them all in yet, you can still turn them in. But the 5 programming assignments will be the basis for grading for this class. Okay. Um, so we're going to look at this sorting, which is an example. Now, sorting by itself is not an example of using closures, but we're trying to do generic sorting, a certain style of generic sorting, and closures are a good way to solve this problem of sorting in a generic way. And a language like Scheme makes good use of closures to solve this problem. So let me real quickly go kind of review for you with the idea. I'm sorry. We've got a data structure and we want to sort it. And the data structure has different fields and we want to sort on this, maybe this field, or this field. Now, in this data structure, I actually purposely made this, like these are 3 different types here: string, int, and double. And we'll see that that's on purpose because that actually causes a little bit of problems for Java to have these things be different types. Okay, so here's the sorting algorithm. But this sorting algorithm is, we say, parameterized by a comparator. Okay, so remember, if we go back, we see this idea, what we use this. Remember how we talked the other day about how a function actually can take more than just data as its input. This is the really deep idea, is that a function can be parameterized by data, the type of the data, and a way to manipulate the data, a behavior. So functions can be parameterized by data, type, and behavior. You're used to that. That's what math does. Function takes data. The function takes in numbers. But in modern programming, like here, the sort function in Java is a generic function. It's got a type parameter out front here. Now, notice that the type in Java's syntax, the type parameter sits out in front of the function name. It looks like it's a return value. And this causes a lot of confusion in people who aren't used to this. This guy looks like a return value. Now, this function it could be returns void because it sorts the array and actually doesn't. So the return type is actually void. This guy sitting out in front here is the type of the data. Okay. Then there's this other parameter, which is the behavior parameter, which says this is how you compare things. Okay. So the sort function has data, behavior, and type information passed to it. Okay. So here, Scheme is not a typed language. So Scheme just kind of completely ignores the idea of type information. Okay, now that's dangerous because you can see in Java that the type of the data has to match the type of the comparator. Java makes sure that they agree. In Scheme, This is the data. It's a list of things. This is the thing that knows how to compare the items from the list. It's up to me to make sure these guys agree. If they don't agree, my program will crash. I will not be warned ahead of time. My program will just crash when it gets to the code. Yeah, it'll whenever if I have a list that and a comparator that don't agree, when I call the sort method, when I call sort, then I will at runtime I'll get a runtime error because this comparator won't match this data. Schemes like that, JavaScript is like that, and C is like that. Even though C is thought to be a strongly typed language, it isn't. C is not. C is actually no better than Scheme, and C is a typed language. You do have to declare the types of everything, but it's not a strongly typed language because the C language can't tell when these guys aren't agreeing with each other, because C isn't as sophisticated a language as Java and C++ are. Okay, so this type information is both a blessing and a curse. We'll see in a minute as we go along today where it becomes a curse, and we'll see how it becomes, it's a blessing in that it prevents you from having runtime errors, but it does make things more complicated. We'll see how in a minute. Okay, so here's my sort function. It's parameterized by the data and then also by the comparator, but not by types in Java. Okay, in Racket. Okay, this is the insertion sort. Okay, here's where now here I parameterize the sort here. There's the comparator. It's a lambda expression. I have to tell my sorting algorithm, sort this list, and then I say, here's the behavior I want you to use. I just define it in line. I just define, as I'm going along here, the lambda expression that says, here's how I want you to compare items. I want you to compare, in this case, it's going to take a country item and get its area, and take another country item and get its area, and then compare them by less than. So it's going to take two country items, get their area, and compare them by less than. Okay, so that's just written out there. How it's there, I describe how the sorting is done. Okay, and then there's a bunch of these. Notice that there's a lambda expression for each one of these. Okay, but this is kind of a lot of code to write here. Okay, so scheme programmers say we can make this a little bit better. We can abstract out the manufacturing of that behavior. So we will create comparison factories. Okay, so I'm going to do it in a couple steps. Notice that there's a lot of redundant code. From the point of view of programming, the goal of all programming languages is to remove redundant code. If you look here, that line looks a heck of a lot like that line. They only differed by that column there. And these two lines look a heck of a lot like these two lines. They differ in, well, this is get A, this is get P, but that's not a big difference. This is a get A, this is a get P. This one's using less than, this one's using greater than, okay? And this one's using a string version of less than and a string version of greater than, and get N instead of get A or get P. So there's a lot of redundancy in that code. You should be able to get rid of redundancy. The modern point of view of all modern programmers is how can we abstract out redundancy? Okay, so the factories are going to be our where we abstract out redundancy. So first I'm going to factor out the less than, greater than redundancy. These two lines only differed by this or this. So that should be a parameter. I want to say something like, I want to build one of these, but I want to tell you whether to use a less than or a greater than. So I've got two of these things, and I want to build two of them, but one time in one of them there's a less than there, another time there's a greater than there. So I'm going to define something that makes a comparator, and it's going to take a lambda. It's going to take a function which is either less than or greater than, and then it's going to build. See that guy there? That guy is this part here with the less than, greater than abstracted to be fn. See, fn is the function that knows how to do either less than or greater than. So this line here abstracts out that line there. Now, then down here, I have to do this 3 times because there's really two. There's two things I have to factor out here eventually. Right now, I'm only factoring out the less than greater than. So down here, here is the thing that factors out the less than greater than out of that line of code. See, it uses get p, but it factors out the less than greater than into the parameter of the make comparator. Right? Then I factor out of these two lines their comparison operator. That's this one here. So I've got three factories that know how to factor out the less than greater than. Now, here I call my functions with my, now notice that this code is a little bit less redundant than this code up here. I make compare by area with less than, or make compare by area with greater than. That takes care of these two cases. Now I make compare by less than, make compare population by less than, make compare population by greater than. Okay. So this is more compact than that one is, but it's still got redundancy. You know, this one's comparing by area, comparing. See, there's a repeated piece of code there. And then these look a lot alike. Make compare by area, make compare by population, make compare by name. That's because there's this other redundancy over here. The get area, get p, get n redundancy. They just play the same role. It's a get method. You could get the area, get the population, or get the name. So why not abstract one more time into a make comparator that takes both how to compare and what to compare on. How to compare less than or greater than, what to compare on, what field to work on. So now if you look, this line of code abstracts out all of these lines of code up here. It abstracts out both the less than or greater than in function and the get a, get p, get n in what I just called get. So you pass to this function what comparison operator to use and what get function to use, and it builds the lambda expression. And now you get very elegant code. Okay, you can sort on less than greater, less than on get area, greater than on get area, less than on population, less than on population, string comparison on names, string comparison on names. Okay, so now I've gotten this thing really compact and elegant. Okay, I'm using closures because this guy here is a very open expression. Okay, function, see, the lambda expression starts here. That's my final lambda expression. C1 and C2 are bound in this lambda expression, but function is bound in this would be the closure that binds function, and get is bound by a closure to here. Okay, so there are four variables in here: function, get, C1 and C2. C1 and C2 are local variables, and function and get are non-local references. Oh, actually, I should have said function and get are. Forgot to update that. So function and get are non-local references. Okay. 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 So this is making use of the fact that the scheme can return closures. It can return this function here as the return value. So this thing returns a comparator function, but that comparator function is a closure making reference to this thing here and this thing here, which are passed to this function and then are accessed by the return function using its closure. Okay, this is real compact code. If if I if I if if I trim this down, like I can get rid of this part here. This was the intermediate step. Okay, here's my really generic sorting function. My scheme code looks like this. If I take out the comments, my scheme code boils down to just this. Okay. Define the data structure. define the sort method, define a couple little helper functions, the factory for constructing comparators, and then do the sorts. Okay, so it's very very little code here, and actually I don't need to define the sort here. I could have used the library's built-in sort. Racket, of course, has sort built into its own libraries. I just chose to define my own sort here. So in fact, I could really just delete this too and use Scheme's built-in sorting function. So then what I would be defining is just the data structure I want to sort, the factory for building my comparators, and then do my sorts with my comparators. Okay, so that's very compact code. Now let's turn this into Java. Okay, and we're going to see an explosion. Well, okay, let's turn this into Java and see what happens. Okay, in the folder on sorting, here's the Racket version. I translated it into language 9. Just show you real quick. Language 9 is a baby version of Racket. I mean, we've really got a fairly sophisticated language here. Language 9, if you look, there's Racket. Language 9 is almost exactly the same thing. I purposely wrote them to be like lined up the code. There's not much difference between the Racket and language 9. So you've seen now how to implement, like you can look at the code for language 9. You're seeing what was state-of-the-art code in like the 1970s. Yeah. In the 1970s, the interpreter for language 9 was basically kind of state-of-the-art. Okay, now they have compilers for Racket. So we really should have a compiler for this, but that's way beyond what one course can do. Racket is now compiled, not interpreted, but you're seeing the core idea of, now our language is not the full-blown Racket. It can do this amount of Racket. There are parts of Racket that our language can't do, but you can see that it's the core of a functional programming language. This language, we can mimic quite a bit of functional programming in our language 9. Okay, now what about Java? What about when we turn to Java? Okay, so Java requires a gazillion. It turns out that there's no one way to turn this Racket into Java. Okay, so we open so there's the Racket code. There's no one way to turn this Racket code into Java. Depending on the style of programming you want to use, and depending on whether you want to use slightly more older Java or try to use ultra new Java, you end up with a gazillion ways of doing this. Okay, there's well, in Racket, we've actually done it 3 ways. So let me go back to, I deleted the, in Racket, we were actually doing it 3 ways. Let me actually get the original Racket file. Because that's why there's 3 folders here. There's one Java way to mimic each of the Racket ways. Okay, so here's the original Racket code. Let me just copy it. We've got one way was to build the comparators by hand. Every time you sorted, you built the comparator in place. So we built the comparators, literally spelled out exactly what they do. No factory methods. So that's one style, no factory methods. Then the next style was a factory method that took 1 parameter. As an intermediate step to building the better factory, we have 3 factory methods that each take 1 parameter. And then we have the best solution, a 2-parameter factory method. So we did 3 ways. Okay, so in Java, this folder doesn't have a factory method. This has a 1-parameter factory, and this uses a 2-parameter factory. Okay, so now this is the case that looks like this, and this is Scheme. Here it is in Java. Okay, now in Java, I'm spelling out all the classes I need. Okay, so I need a country class. Okay, In Scheme, I can just spell out what my data structure looks like. I don't have to define ahead of time a country data type, but in Java I do. So I have to spell out what my country data type is. So there's the country data type, okay? Then I have to spell out what all my comparators are. So there's the 6 comparators. I need 6 different comparators, and I have to spell them out. So like this one is compare area ascending, compare area descending. So I don't have, in this is doing very old-fashioned Java. I can't use a lambda expression, so that code has to be embedded in its own class. Okay, so there's the class that does that. See, that line of code there is implemented by that class there. Notice that what would be half a line of code in Scheme in this style of Java becomes a class of 10 lines of code. Okay, so there's the, and I need to do that for 6 comparators. Okay, then after I've defined my 6 comparators, I have to write the code that actually does the sorting. Here's the list of, see, there's, now, see, in Scheme, I can just say, there's my data. Here I can say, here's my data, but I have to tell Java exactly what it looks like. So I have to have this class, country class predefined, so I can say, oh, this is a list of countries. Whereas in Scheme, I can just say, here's my data. Okay, but in Java, I have to say, I have to define what a country looks like, and then I can say, here's a list of countries. Okay, then here's a sort, but I can't build the comparator on the fly. I have to have the comparator pre-written in its own class file. So there's sort with a new comparator. Just like here, I'm saying sort with this comparator. I'm building the comparator on the fly here. Here I instantiate one of my comparator objects. Okay, so there's the 6 sorts. Okay, so it's in this style of programming, this 6 lines of code in Scheme turn into a whole folder worth of files. Turns into this whole folder worth of files here. Okay, turns into this whole folder of files. Okay, that's kind of messy. So that's a very old-fashioned way to do it in Java. Okay, now in Scheme, the next step was to do a one parameter comparator factory. Okay, so in Java, there's another folder that does one parameter comparator factory. So there's the 3 comparators. See, there's the 3 factories. See, here's the 3 factories in Scheme. Here's the 3 factories in Java. You can look at one of them. It's a class that the constructor takes in a function point. Well, it takes in what I'm calling a functor. In Java, you can't pass functions around. You always pass objects that hold a function. That's what an object is, something that holds a function. When an object, its goal is to only hold one function, we sometimes call them functors. Objects whose only goal is to hold one function. The goal of this object is to hold the less than or greater than function. So I pass to this constructor the thing that holds whether I'm doing a less than or a greater than operation. And then on each country, I get the area and do the, now notice that this looks a little bit like Scheme. See this line of Scheme here. If you line your code up carefully, look, the ideas are starting to look similar. I apply the function parameter to get area on country 1 and get area on country 2. So here's get area on country 1, get area on country 2, and there's the function parameter, though it's called in a slightly odd way because this is Java. So fn is the object holding the function fn. See, I have to use this funny notation. This is an object holding my function. Here in Scheme land, it's just a function. I don't have my function sitting in an object. My function is a function. In Java, my functions have to sit in objects, and I just called the object fn and called the function inside of it fn. You might quibble with that's maybe not a good style of naming, but there's no real great way to name these things. So I use the name of the object is fn, and it holds a function called fn. So there I call my parameterized function, just like I'm calling my parameterized function here. What is a closure in Scheme is a field in an object in Java. This is the key concept here. In classic Java programming, where you would need a closure in the functional programming language, you use a field of an object to remember. See, this is a non-local reference. See, it's not local to that function. This is a non-local reference. It's from that closure. This non-local reference is to that field. Fields become the closures of your functions. The object and its fields close the function. That's the design strategy that the Java people decided, that fields and objects are good substitutes for closures in functional programming. 20 years later, they decided that wasn't a great design decision. Now they're back to trying, and we'll see as we go along, we can come pretty darn close to doing this in Java. Not quite perfectly, but we can come really close to doing this in Java. So we'll work our way up to it. But this is the original design of Java said, okay, where a functional language needed a closure, we'll give them a function holding a function, we'll give them an object holding a function, and the object's got a field that closes the function for you. Okay, so there's the one parameter factories, okay? And then if you look at the use of them, there's the list. I sort on a comparator that takes one parameter. So there it is. There's the, see, there's this guy. Sort countries with a factory that takes one parameter. Now notice in Scheme, I can do something very elegant. I can just say, make compare by less than. No way in the world Java is going to let you put less than there and pass less than as a parameter. Java will never be able to do that. That's just way too abstract for Java. You can do this in languages like Scheme and Rust and Haskell. Java doesn't let you do that. So I have to wrap the less than symbol in another functor. I can't pass less than, so I have this extra boilerplate code. I have to create these little functor objects that basically just hold greater than and less than for me.
I have a question.
Yeah.
Would it make sense to do something in Java, say like make a static analyzer that does a little bit more than just analyze? It will just generate the syntactic sugar for something like that. So you have some boilerplate conversions of.
That's actually what their compilers do. When I show you the real, the modern, ultra modern Java, everything you're looking at is going to be syntactic sugar.
Oh.
And yeah, they pretty much kind of take that point of view. But it's a little bit more complicated than that. But yeah, that C++ templates take that point of view. You know, that when you write code, the compiler just rewrites it for you into something that would be a little bit nicer. Or it would be, you know, it writes the complex code that you don't have to write.
So why couldn't we why couldn't we make something like that for Java that will just give us normal lambda expressions?
We almost have
normal closures.
I'll show you. Wait till we get to the end. You'll see how close Java gets to this. It gets very close. It does have closures, but they have a couple limitations. So wait till we get to the end of the story. It's a real fact. I think this actually worked out real well. I spent a lot of time writing and rewriting this, and I think I've got it now to where it really tells a really good story of the history of Java. So when we get to the end, you'll see what Java can do compared to Scheme and Haskell and what it can't do. Okay. And you're right that underlying a lot of this is basically syntactic. The compiler wants to translate very terse code into very elaborate code. This is right now you're seeing the very elaborate code. So you're
Hmm.
seeing what the Java language really thinks is going on in the background. But the modern Java can let you write almost scheme-like code and get this stuff happening automatically.
Oh.
Okay. All right. So now let's look at the next folder. In the Java world, the next folder was the two comparator folder. Okay. So here's now the the comparator that takes two. There's a single comparator that takes two parameters now. Okay. And the two parameters are fields in a class. The racket version, the comparator takes two parameters. Well, in the scheme version, the comparator constructor takes two functor parameters. So you cannot give this guy functions directly. You have to give him functor parameters. So that's an object holding a function, and that's an object holding a function. The constructor remembers them. Then these guys are the closure, essentially. Then here is the comparator. The comparator makes use of this non-local reference and this non-local reference. Notice that you have to do really weird code, get.get, because get is the object holding the get method. And function is the fn is the object holding the fn function. So I chose to name the object with the name of the function it holds. That was just a design choice of me. So the code is fn.fn of get.get. Okay. All right. So there's the two parameter factory method. Okay. And then when you use this in Java, it starts looking pretty good. I sort on a factory that takes in two parameters, and I've now abstracted out, so I can sort by just passing the factory two different functors. But I have to write all this boilerplate code that supports all the functors. The main problem here is all this functor stuff. There's all the functor stuff. There's the greater than, less than on doubles, and the greater than and less than on strings, and there's the get functor with a get area and a get name and a get population. So I have to have boilerplate. This is actually the real problem. These should all be lambda expressions. And since in this early style of Java programming, I don't have any lambda expressions, this part and this part look real nice. They are pretty good. The real burden is what should be lambda expressions have to be objects holding functions. Okay, so there's a lot of boilerplate code there. But these two parts look actually pretty good. You call the constructor with two parameters, but the two parameters are themselves constructors of functors. Okay, so the final code doesn't look too bad from the point of view of the Java language. The library looks kind of messy. The library's got all this functor stuff thrown all over the place, but you do at least get to write fairly elegant code. Two parameter comparators. All right. So this version of Java is not bad. Okay. This version of Java with the two, except for this, all the functors, the heart of it looks pretty close to Java. Okay. Now I continue. Now remember, there's three versions here, but this was putting everything in its own file. You can, if you want, put everything in one file. So all these files are combined into that one file there. Okay, so this is a style of programming. All those files that were in that folder are now private classes in this one file. And the class that holds the main method is the only public class. So there's the public class and all the private, what we call private classes. Nobody programs in this style. This is a really bad style of programming, but I wanted you to see that, okay, you can do this. You can put all the classes in one file. This is very bad style, okay? But you can do something that Java does do. You can move these see these classes? You can progressively move them farther and farther into the main method. the philosophy is that if you have a class that's only used in one program, you really should, okay, let me compile this. Notice that when I compiled it, I generated tons of class files. Those class files are essentially in, they're cluttering up. It's kind of weird. They're not in the public namespace, but they're in kind of a never land. It's a little bit weird how they look like they could be in the public namespace, but they're not really. Like, this is not a public class now. This class is a private class inside this file. So this is considered kind of a bad way to do things, okay? Because, you know, these classes are kind of, they look something like they're public, but they're not quite public, all right? So Java has a better way of doing this. My point of view, my feeling here is that these classes really belong to this program. So they should be embedded in this class here. Since they're really used by this program, these classes should be embedded in this class. Well, you can do that in Java. That's the next version of this. I'm going to go from what we call private classes to what are called static nested classes. So I'm going to move the private classes that are outside of the public class inside the public class and make them private to the public class. Here's what the code looks like. This is called static private classes. Let's see. The classes moved inside. See, they're indented. They're now inside that class, but they are static. So these are called private static classes. Okay. Now what they do is they really truly say that this class is a helper class to this class. They really belong to him. Okay. Now let me do something here. Let me get rid of delete the class files. Now let me compile this program here. When I compile it, see how I generate a bunch more classes? But now it's real clear that everything in this program belong to that program. Notice how all those static classes have their name as, oh, I'm part of, see, I'm a static class, but I'm part of this guy. See how Java names them. So now if I look here, I see essentially that I really have defined classes that are inside of a class. So I don't have a bunch of classes polluting my, I do have a bunch of classes, but these classes are now named in a proper way to say that they're helpers, okay? So sometimes people program in this style. This is a better style than having private classes, okay? But this is still kind of weird. I can actually move these classes even, if you think about it, these classes aren't really being used by this class, they're being used by this function. These classes aren't really paying a service to this class, they're paying a service to this method. Java lets me move these classes into a method. So that's version 3. See, notice I'm giving you a tour of what the Java language can do and how you should think of the Java language. I'm now going to move my classes even farther inside my code. Instead of them being static classes in a class, they're going to be what we call inner classes in a function. Okay, so now
is that extreme degree of like localization of
no,
functionality a good idea?
yes, it's ubiquitous in Java. We're heading towards a design pattern that's ubiquitous in Java. This design pattern is not considered very good. This design pattern is considered terrible. Nobody uses it. This design pattern is considered good in some cases. The case would be that this class pays a service to all the functions in this class. See, if these classes are really useful to all the methods in this class, then they should be in this class. But right now we have a situation where these classes really pay a service just to within this one main method. So we're moving them where they belong. Localization is always a good idea. That's a modern programming paradigm, is that you should localize code to where it belongs. So now we're going to move our classes into the main method, okay? Now they're called inner classes. Now notice that they lose any decoration. Notice that they went from having no decoration, but they were outside the class, to being inside the class with a static decoration, to being inside the method with no decoration. But now they're nested one layer deep. Now they're nested inside of the main method. So these are called inner classes. Okay, these are called inner classes. All right, all right. Now, it turns out that they're still not where they belong. Okay, in a sense, take this class here. He actually is being used by that line of code. And also again by that, well, he's being used by that line of code and by that line of code. If you want, now this becomes, now we're doing a step that you may quibble with, and sometimes it's actually a good thing to do. This code is really being used here and here. Let's move it there. We're going to move this code into that line of code. Now, in a sense, we're mimicking Racket's sense that we move the constructor, we move these, we call the comparator right there. See, there's our comparator factories. So it's a little bit like saying that you want to call these functions inside here. But what we're going to do is we're going to actually take this constructor, this class, and embed it in the middle of this line of code. We're going to embed a class definition into a line of code. Now I'm going to skip an example. I'm going to go from 3 to 5. I'll explain in a minute what 4 is. So I'm going to go from 3 to 5. And you start getting code that's a little bit unreadable, but it's ubiquitous in Java. I took this class and embedded it where he was used. So it looks like this. Countries sort by, there's the comparator to sort by. This is now called an anonymous inner class. This is unreadable code and it's ubiquitous. This is actually considered good programming style in Java. Okay, so I have moved the comparator to where it really is being used. Okay, but it has a tendency to see, you get this weird code like semicolon, open brace, semicolon, parentheses, brace, brace. Yeah, what I have here is I'm constructing a comparator object and I'm creating a new comparator, and then here I'm actually defining what the comparator looks like. Okay, this, Java calls these anonymous inner, okay, these were called inner classes, but they're not anonymous. The inner class is this guy. See, the inner class has a name. So now, notice that this name is gone now. And when I look at this code, there is no name country comparator by population or country comparator by area. That name is gone. I'm just saying I want to sort with a comparator, and then here's the code for what the comparator looks like. Okay, that's a style of programming. Now the trouble with this is it's actually not so good, because see how this comparator by area was used in 2 places? So when I move the comparator into this code, I actually get a duplication of code. See, it's copied here and it's copied here. So the problem here is that I need this comparator in 2 places. If I only needed it in 1 place, this would be a good idea. So if you have a private class, an inner class that's only used in 1 place, you move it to where it's used. But if that private class is used in 2 places, then this is not a good idea. So the step from 3 to 5 could be a good idea or might not be a good idea, depending on whether that private class, that inner class, I shouldn't say private class, inner class. If that inner class is used in multiple locations, like it is here and here, it's probably better off left by itself. Here's the inner class, use it here, use it here. On the other hand, if it was the case that the inner class was only used once, you should move the inner class to where it's used. But the code becomes very hard to read. Now here I moved it to 2 places, so I'm actually I'm self-defeating myself. I'm back to duplicating code because I moved that private class into 2 places. Here it's calling get area with a less than functor. Here it's calling with a greater than functor. See, the difference was, the only difference between this block of code and this block of code was this less than here and this greater than here. Okay, so that's not great, but it's showing you a style of Java that you can move code to the location. You can move whole classes. You can move whole classes from where they're defined to where they're needed by using what's called anonymous inner classes. Okay, all right, so back to the original Java folder. All the code in this folder can be moved into one file 5 different ways. The 5 different, it's documented in here if you read this. The documentation, this is private classes, static classes, inner classes, then 2 ways of doing anonymous inner classes. This is named anonymous inner classes and unnamed anonymous inner classes. Okay, so if you look in here, there are, in the folder are individual public classes. Then I use private classes in a file, static nested classes in a file, named inner classes in a file, named instances of anonymous inner classes, and then anonymous instances of anonymous inner classes. That's the last example we looked at. These are paradigms of Java programming. If you're reading other people's code, you can look at their code and you can say, oh, he's using this style, this style, this style, this style, this style, or this style. Any given code in Java is either using anonymous instances, anonymous inner classes, named instances of anonymous inner classes, named inner classes, static nested classes, private classes, or individual public classes. You know, these are the 5 styles of structuring Java code. In this example, that's the sweet spot. That was the sweet spot because that was where we have these inner classes. Oh, I'm sorry. Yeah. Where I lost myself. Oh yeah. Here we have. These are the inner classes, and each one is being used several places. So I don't want to move them directly to where they're being used, because if I move this class, oh, I'm sorry, that's the yeah. If I move this class to where it's being actually used, I'll have to move it several times, and then it just becomes redundant. Okay, so the sweet spot is the version 3. Same with this one here and this one here. The sweet spot are the version 3 ones. The version 4 and 5 ones are a little bit overkill because I'm taking an inner class and moving it to 2 places where it's being used. So that means I have to duplicate it. So I'm showing you what the code looks like, but the 4 and 5 versions actually aren't really good versions in this case. Okay, so this is no factory method, 1 parameter factory method, 2 parameter factory method, private classes, static nested classes, inner classes, anonymous inner classes that are named, unnamed anonymous inner classes. So there's the 5 styles. But these all with no factory method. Then here a 1 parameter factory method and then a 2 parameter factory method. Okay, notice that there's how many different ways you have to write Java. Okay, now let's look at, oh, actually, let's look at this one. This is the most elegant way to write the Java version of the two-parameter constructor in the classic style. No lambda expressions yet. Okay, right. So this code comes. Oh, let me. This code here comes pretty close to mimicking this code here in Scheme. This is the code in Scheme that has a factory that takes two parameters and gives you back a closure that references the two parameters, and then you call the factory method with two parameters and you do your sorts. Okay, over here in Java, let's look at what this is. This is the classic Java way to get close to this without using lambda expressions. Okay, there's the data structure. Down here is, well, I have to tell Java what a country looks like. So I put that down. I keep that as a private class. That's just a private class down here. Okay, so there's the private class that says what a country looks like. All right. Here's the code that actually does the sorting. Sort countries using a comparator that takes in two functors. Okay. This is a compare. Now I have to write this generically. I'm comparing on doubles because I'm comparing by area. If I'm comparing by population, I'm comparing on doubles. Actually, I should add the populations int. I actually goofed this up. Now I realize that the area is well, one of them was a double and one of them is an int. Actually, I forgot which one I did. Let's see. Let's go back up here. Oh, area is an int, and population is a double. So I really should have made these. For area, it should have been double, and population, it should have been int here. But names are strings. So I'm comparing on strings. So then I have a string comparator here, and the get name returns a string. See, Java's keeping track that this type here, and this functor here, and this functor here all have to agree with each other. Get name returns a name. So I should be comparing string. Get name returns a string. This guy better compare strings, and here I have to declare that I'm comparing on string data. So Java makes me get all my ducks in a row and make sure that I have all kinds of agreement here between this functor, and this functor here. The comparator compares strings, whereas these guys over here, this is a comparator of doubles. This is a functor that compares doubles. This gets a double, and I'm building a comparator of doubles. So I have to declare carefully that everything's all the data types are aligning. Up here is the let's see, where is it? Here's the actual factory. Pretty compact. Now this is a inner class. This is inner class with two fields. Now remember, fields are playing the role of closures. There's the actual comparator function. Just like here, there's the actual comparator function. That line of code, I can line these up. That line of code right there maps to, well, in Java it has to be written a little bit more verbosely. It maps to these two lines of code here. Okay? But see, that line of code there maps to those two lines of code there. You can read a parameter function, get on a country, get on a country. A parameterized comparator, a parameterized get on a country, a parameterized get on a country. Notice it's very similar code, but the actual functions are wrapped in objects, whereas here the functions are functions. Okay, here the functions are all carried along by their functor objects. And then I have to do this boilerplate code of defining my functor object. This is the truly messed up part of this code. I have to say what all my functors look like. And I have to do them very carefully. I got to get the generics just right. So I have to get the generics on these guys correct. So I have an abstract functor that's a generic functor, and then I have implementations of it, one that does double, another one that does double, and one that does string. Okay, so it's a bit of code to write. This wasn't trivial to write. Notice that This is the heart of it in Scheme. And there's the heart of it in Java. It's actually looking pretty good. As far as the heart of the Scheme and the heart of the Java, they don't really look too bad. There's a pretty good comparison. The problem is these functors. And the functors are there because Java, two reasons. Java can't have a function by itself. A function has to be stored in an object. A function has to be stored in an object. And then the other thing is that Java requires you to line up all your types. So I need to say all this code, a lot of it is basically telling Java exactly all the types that everybody has. Scheme doesn't make you line up the types, but Scheme can blow up in your face. If that comparator doesn't agree with, if that thing doesn't agree with that thing, this comparator will blow up on you. If this thing, like if you pass the string comparator here, but this was getting areas, you'd blow up. Scheme wouldn't, you can actually, you can try it in Scheme. Take this guy and put him there. Run this code and you'll blow up at runtime. Not at compile time, at runtime. This comparator won't work on a string. Even though it would look okay, the code would look okay, it won't work. See, you have to use a string comparator here because this guy's really returning a string. But you won't know that until runtime. Java is making me spell it out at compile time with a lot of pretty verbose code. But the heart of it there looks pretty good compared to the heart of it here. Okay? All right. So now let's look at what Java can do. Now let's switch to ultra modern Java. And it's actually kind of interesting to see what ultra modern Java can do. Okay. I'll skip over the no factory version, and the factory takes one parameter, skip to the two factory method, the really good version. This is the version in Java that's trying to mimic mostly. This is the Java program that's trying to mimic the Scheme program. Okay, so let's look at it. Now, okay. Here's the data to sort. Here's the data to sort. Java makes us say what a country looks like. That's down here. Okay, but that's not really that important. There's the data to sort. There's the data to sort. Okay, skip. I don't need. Skip over the sorting. Okay. Notice I have a bunch of helper functions here. Well, here I have to. Java doesn't let me, like here these helper functions don't need to be here. I'm just, this one, get name, the name is the car of this list. So get name is just a fancy name for car. And get area is the, area is here. That's the car of the cooter of this list. Notice that get area is just the car of the cooter. So I don't really need these names here. Instead of saying get A here, I could just write car. Instead of get P here, I could just write. I don't really need these names. I just wrote them there because it's a lot easier to read. Get area, get population. But I could have just used these Scheme functions. So these are not there out of necessity. They're just there to make the code a little bit easier to read. Now in Java, these are here out of necessity. This is where I'm defining my functor types. But I'm using lambda expressions. Okay, so notice that instead of defining my functor types verbosely, I'm defining my functor types pretty compactly, and I'm actually using functor types built into Java. So by predicate is a functor type that takes in two numbers and returns a Boolean. So by means two inputs, predicate means return Boolean. So there's the lambda expression. that takes in two parameters and returns a Boolean value. So this lambda expression has the type of by predicate, and it takes in double, double. What I'm doing here is that Java in this util package here defines a bunch of functors for you. So instead of me having to spell out all my functors, I still need them. They don't go away, but Java has predefined functors for you. And now I can define the body of the functor with a lambda expression. So I use predefined Java functors, and I use lambda expressions for the body of the functor. So that saves a lot of code. That saves a lot of what was this. See, all these little boilerplate functors here, where I'm defining my own types for them. Now I'm switching to Java's predefined functor types, and I'm using predefined functor types, and I'm using lambda expressions for the bodies of the functors. So the bodies of the functors are lambda expressions. All right, so this is pretty good. So this is one step that Java lets us do. Java helped with the boilerplate functors by predefining a whole library of functor types. Oh, let me show you this library. It's kind of interesting to look at this library. Here's Java's library of a whole slew of predefined functor types. Okay, and they wrote all this boilerplate code for us, and then they gave these guys weird names like into double function, int unary operator, long binary operator, supplier, predicate, like so they give you, and you kind of search through this list and you look for a functor that suits you. So if you need a functor and you don't want to define your own, you look to see if Java's got one defined for you. Okay, so I was able to find a couple different functors that I could use. Okay, so these are my predicate functors, and these are my get functions. My get functions, I use the function functor, and see, then I use, so get area is select A. So that's a lot like these. So basically, these three lines of code here are playing the role of these three little lines of code here. Okay, in fact, I can actually get rid of these lines of code here. I could have just, where I'm using where I'm using this, I could have used that thing there. Okay, all right, so then here is the factory, but the factory is still written as a class. I haven't written the factory yet as a lambda expression. Here the factory is a function. Here the factory is still written in the old-fashioned way. So I've made a step towards using functors to get rid of a lot of the boilerplate code, but my comparator factory is still a class. Okay, and then here's the 6 comparisons. Okay, now let's make the last step. Let's make the comparator of lambda expression. And this is fascinating because it almost works, but it doesn't quite work. So now we're deep into the weeds of programming language theory. What did the Java language designers accomplish and what did they not accomplish? So let's look at the last step. It's this Java 8 comparator 2 functor version, okay? Here is the factory as a traditional class. It's highly parameterized, a lot of generics. Here's the factory. Here's the factory as a functor, as a lambda expression. Okay, we're back to very unreadable code. Here is, oh, and actually I need three, probably should compare. I don't know whether you want to compare this code to the previous Java version and the Scheme version. So actually I really want to open up all three of them. So it's kind of a, it's a, It's a tough little compare. Okay. I'm going to try to compare three styles of programming. Okay. Here's my racket version. There's the two-parameter compactory. Here's my Java class that's a two-parameter factory. And then here is my attempt at a two-parameter lambda, two-parameter function, two-parameter factory that is like this one. That's a function. Okay. So here it is. This little piece of code here almost matches this code perfectly. Okay. Make compare takes in two parameters, and it returns a lambda expression that takes in two parameters. See, a lambda expression returns a lambda expression. I have a lambda expression returning a lambda expression. Here's the body of the lambda expression that's being returned. That one line turns into two Java lines because the way comparators work in Java. And there is actually, I should have probably put this on its own line to make it look like the scheme. Okay. If I indent it to look like the scheme, it's pretty good. Make compare returns is a lambda that returns a lambda. Make compare is a lambda that returns a lambda. The body of the lambda is one line here. The body of the lambda is actually three lines here, okay, because the way comparators work in Java. What's the type of this thing? The type of this guy is he's a bifunction that takes in two parameters. He takes in a predicate and a get method, and he returns a comparator. So here I'm spelling out the type information of this comparator. So you have this kind of hard to read thing here that says that the comparator is something that takes in two parameters and returns a lambda expression. Its first parameter is a functor, its second parameter is a functor, and it returns a functor. It takes in a bipredicate, which does the comparison. It takes in a get method, and it returns a comparator. Okay? What's the problem? Now notice that I have to declare my types here, where in Java and Scheme, I don't have to declare any types. Here's the problem, though. I need two of these guys. I need one that does string and one that does double, because Java doesn't let you write generic lambda expressions. The Java language, the brick wall they hit in trying to mimic Scheme and Haskell was they could not make lambda expressions generic. Here's what I want to do, and I'm not allowed to in Java. I want my factory method to be generic and take in a type parameter. So I want my comparator to sometimes compare string and sometimes to compare doubles. I cannot put a type parameter into a lambda expression. Okay? I have to say it's either a string comparator or it's a double comparator. Notice I've got redundant code here. This code here and this code here look exactly alike, except this one acts on strings and this one acts on doubles. I should be able to abstract out that double to a T type. Java can't. This is where, and why Java failed at this, I have no idea. You'd have to go deep into the compiler to see what stopped them from defining generic lambda expressions. Now, Haskell can do this. You can do this in Haskell. But Haskell is a typed language like Java. In Haskell, here's what you would do. In Haskell, you would delete this type information here, and you would just type that, just like you type this in Scheme. Haskell would infer the type information. And when it gets here, it would infer a need for a double type. And when you get down here, it would infer a need for a string type. So you could write that one line of code. You would leave ambiguous the types. You wouldn't try to pinpoint them. You'd let the Haskell compiler figure them out. And the Haskell compiler would figure out the type here needs string and the type here needs double. And it would work. Java makes you spell out the types, but Java doesn't let you say that there's a parameter there. So Java makes you duplicate code. So Java almost got to where Scheme and Haskell are. I mean, Scheme does it by ignoring the types, but you can get runtimes errors. If I wrote this in Haskell, the Haskell code would actually look a lot like this Java code, but the Haskell code, I would be able to write this in one, I would write this comparator once, I wouldn't need to write it twice, and I would delete the type information and let Haskell figure it out. And then Haskell would compute the type information on the fly. So it would make one kind of comparator here and make a different kind of comparator here. That takes a lot of theory. Okay, the Haskell compiler took years to write. Now the Java people could go look over the shoulders of the Haskell people. So in fact, they're the same people. The person who wrote, one of the people, see this book on Java generics. See this guy, Philip Ladler. He wrote Java generics. He also wrote the Haskell compiler. So he really knows what he's doing.
Doesn't that guy hold the computer science equivalent of a Nobel Prize for that?
Not him. No, a different guy did. Not him. It was the guy who invented type inference who got the Nobel Prize. He implemented it in Haskell and he tried to implement it in Java. And he came close in Java, but not quite. So the Java people, when they did this, they knew what they were doing. So what stopped them? I mean, okay, you think of it. What do you think stopped them from hitting it like Haskell did?
Breaking old code.
Exactly. They were tacking this on to a 15-year-old language at the time. Haskell was designed from the ground up to solve this problem. Java started with remember Java started with this code here. The new version of Java has got to be backwards compatible with this old code. When they tried to make Java act like Scheme and Haskell, the brick wall they hit was that they could not break old code. And this is as close as they could get to it. It's fascinating to see how close they got.
Why do they have to care so much about breaking old code? Those people running the old code would just be using an old version of the JVM.
No,
why would they care?
The answer is here's why. They want to tack new code onto their old code. That's the actual goal. You've got a code base written 15 years ago. It's got to be added to. Why should you have to write old-fashioned code? Why can't you write new style code and tack it onto the old style code? That's actually the goal of Java.
I was thinking about industrial environments where they just use the same stuff until it breaks.
Right. That's a design choice of the industrial environment. If they have old code, they might tell their programmers, you have to write new code in the style of the old code. But some companies will add to their old code in the new style because it's more productive. Java will let you do that. You could mix and match. You can write new code in the new style and compile it with the old code in the old style. That's the real goal. But that puts a heavy constraint on things. The heavy constraint shows up here. They were not able to make generic lambda expressions. That stopped us from writing a truly Haskell-like comparator factory. But we could still do it in the classic case. Notice that we have one comparator factory in the classic case. So if we use a classic class, we have one comparator. If we use lambda expressions to try to mimic Java and Haskell, we have to use two comparators because we can't write them generically. And if I truly made this strings, ints, and doubles, I would need 3 comparator factories because I would need 1 on ints, 1 on strings, and 1 on doubles. Here I made this double and double. I should have gone back and made this string, int, and double. And then Java would need 3. I could do it in 1 class, but I would need 3 lambda expressions because I cannot parameterize. If you go back to our notion of what it means to be polymorphic, that you could pass data, type, and information. Here's how the way to think of it. In Java, you can do all 3 of these in classes, but you can't do this one on a lambda expression. A lambda expression can be given data and it can be given behavior, but you cannot pass type information to a lambda expression in Java. That type of polymorphism isn't allowed on lambda expressions in Java. It's allowed in classes using generics, but generics can't be used on lambda expressions. So Java hit a little bit of a brick wall. There's where it would look like this, but that's not, you can't compile that. If you try to compile that, Java compiler is going to say, it's going to get to this guy and say, that can't be there. You know, that doesn't belong there. Okay, so it's kind of fascinating. You know, we've really pushed Java to its limit by taking scheme code and iterating through it over and over and over again in Java. We try to get to where the Java code looks as much like the Haskell scheme code as possible, and we see what the limitation is. One last thing to point out is not many people program in this style in Java. This style is ubiquitous because it works. This style, you know, people use it where it can be used. It's a little bit, it's got, you can see that it's got a limitation. The Java closure, the Java notion of closure and the Java notion of lambda expressions, they are lacking something. So, and also the code's a bit of a bear to write. This was not easy to figure out. I mean, it took me a little while to get these functors all lined up. You know, I had to go through this list of their functors and try to find which functors would work for me. You know, and it took a little bit of effort. It's beautiful code. It's beautiful, elegant code. You know, but it does lack the parameterization. It does lack the genericity. Here was what the last homework assignment was going to be, but we needed a couple weeks to do this. To have you duplicate this in a language of your choice.
Oh.
Like, do this in C++. How close can you get? You know, do this in Go. How close can you get? Do this in JavaScript. How close can you get to the scheme? My guess is, I've done this in a couple languages myself. I haven't done it in C++. I think C++ will hit the same brick wall that Java did. I bet you'll be able to get to this, but I bet you can get to this in C++, but you probably can't parameterize over this guy. But it'd be interesting to know whether C++ can do this last step or not. Rust, C++, Go, Scala, JavaScript. I think JavaScript should be able to do exactly this. I'm pretty sure you can do this exactly in JavaScript. So I mean, that was my idea for the last homework assignment, but it would have needed a little bit more time. You know, for each, you have people pick a language. And if you're interested, if this is a challenging, good little benchmark program. If you want to learn a language and learn what its generics are capable of, do this one. Do this sort in your chosen language and see what the language, how close it lets you get to that code there. There's your benchmark. And actually another benchmark is the Haskell version. Scheme and Haskell are the two benchmarks. Scheme for a non-typed language, Haskell for a typed language. Take your chosen language, how close can you get it to be either like Scheme or like Haskell? Scheme doesn't need to require you types, Haskell does require types, okay? So that was my idea for the last assignment, but there isn't time for it. But if you want to really, if you pick a programming language and you want to call yourself an expert in the programming language, you should do this example in your chosen language. You should be able to, and also
Okay.
do this string, int, double. Do 3 types here. I'm going to actually go back and I'm going to add the 3rd type because actually I only did it string and I did both these columns as double. It should have been string, int, double. And that would have made my Java code need a one. I would have needed now 3 comparators instead of 1 comparator. Okay. All right. So we've gotten pretty far in programming language. We've seen the theory. We're not doing the theory. We're seeing where the theory leads us. So in these examples, we see that there's a need for a theory. Why can't Java do that? From a programmer point of view, you just say, oh, I can't do that, so I don't try to do that. So I do this instead. But if, as someone who wants to understand computer science in its more general sense, you might ask why, what needs to be done in the implementation of the language to make this last step work? How do you make lambda expressions generic? And it wasn't an easy thing to do. The Haskell language worked hard to get to where you could have truly generic lambda expressions. Okay, so we've gone over we'll quit. We're done now. If you haven't turned in the last homework assignment, the last homework assignment, you can turn it in up. I forget what was the due date I gave you for
The
it,
20th.
which is what? Oh, it was actually. Oh, it's already been turned in. Yeah, it's already due. But if you haven't turned in the last homework assignment, I'll accept it till the end of next week. Okay, so you can continue to work on. If you haven't turned in the last homework assignment, keep working on it. But otherwise, we're done. Okay, but look at this code. I think this code is really, this code tells a really good story.